Data centers supporting large language models draw immense electrical loads. To function, they require energy that is entirely firm, carbon-free, and continuous. Firm power means the generating capacity runs 24 hours a day, 7 days a week, regardless of weather or environmental variables. While solar and wind generation are carbon-free, they are inherently intermittent. Relying on them for the baseline power of a massive data center campus requires an unfeasible scale of battery storage to bridge the gaps in generation. Natural gas plants easily provide that necessary firmness, but burning fossil fuels violates the strict zero-carbon operational commitments made by these operators. This leaves nuclear fission. It is the only known technology capable of delivering firm, zero-carbon electricity at gigawatt scale. That physical reality is turning technology companies from software providers into anchor customers in the heavy energy sector. Conventional large light water reactors, designs like the Westinghouse AP1000 or the French EPR, are massive. A single unit typically generates between 1,000 and 1,600 megawatts electric. This image shows the overwhelming footprint and heavy crane logistics required for these conventional builds. The recent history of Western construction at this scale serves as a cautionary baseline. The VC Summer project in South Carolina was abandoned in 2017 after $9 billion were spent without producing a single watt of power. The Vogtle expansion in Georgia finally came online in 2024, but at approximately $35 billion, nearly doubling the original cost estimate. These severe cost overruns and timeline delays have rendered traditional site-built nuclear reactors almost impossible to finance in Western markets. Small modular reactors, or SMRs, are the counterbet. These are standardized units intentionally rated below 300 megawatts electric. By abandoning the custom stick-build model, SMRs move fabrication to the factory floor. The plant is assembled on site from prefabricated modules. It trades the economies of physical scale for the financial predictability of economies of multiples. Moving from massive site construction to modular assembly looks like this. Inside a reactor hall, massive components like this cylindrical containment vessel are maneuvered into place as standardized units. To shrink a reactor down to this size, engineers must rethink how they manage decay heat. This is the residual thermal energy that continues to generate even after a fission reaction is completely shut down, which requires constant removal. Traditional large reactors rely on active safety systems. They use complex, electrically powered pumps to circulate coolant and carry that decay heat away from the core. This diagram outlines a passive safety system in an SMR. Instead of mechanical pumps, coolant circulation relies entirely on physical laws. Hot coolant naturally rises by convection, sheds its heat, and the cooler, dense liquid falls by gravity in a continuous, closed loop. Notice what happens when we remove the active pumps from the system. The loop streamlines. We drastically reduce the number of critical mechanical fail points in the reactor design. Pressurized light water SMRs, like NuScale's Voyager and the Rolls-Royce design, use this exact passive philosophy to compress conventional reactor physics into a much smaller footprint. Passive safety enables the modular build. Without the requirement for active pumping systems, the reactor is small enough to manufacture in a controlled factory environment. While light water designs scale down existing technology, other engineering teams are reviewing flow paths for completely different coolant architectures. One approach is the sodium-cooled fast reactor. Liquid sodium possesses specific thermodynamic properties. It has an extremely high boiling point and superior heat transfer capabilities compared to water. Handling molten sodium requires highly specialized infrastructure. Here, a technician operates a test loop where liquid sodium flows through an observation section, visible by its faint orange thermal glow. Because sodium doesn't boil until it reaches very high temperatures, the reactor can operate safely at near atmospheric pressure. This eliminates the need for the massively thick, high-pressure containment domes required for water-cooled plants. The TerraPower Natrium design uses this architecture, targeting a baseline generation of 345 megawatts electric. Natrium also integrates a molten salt thermal storage tank. This large reservoir sits adjacent to the reactor and acts essentially as a massive thermodynamic battery. This thermal storage allows the plant to throttle down during low demand, or surge its output up to 500 megawatts for several hours. By decoupling the steady thermal output of the reactor core from the variable electrical demand of the grid, the plant achieves load-following stability. Advanced reactors still require heavy industrial manufacturing. Machining a thick-walled steel forging for a reactor pressure vessel demands exact tolerances under high physical stress. Some designs push operating temperatures even higher. High-temperature gas reactors, like the X-Energy XE100, use helium coolant to safely operate above 700 degrees Celsius. Operating at extreme heat opens industrial applications far beyond electricity generation, directly supplying process heat for heavy chemical manufacturing and large-scale hydrogen production. Fluoride salt-cooled high-temperature reactors, currently being developed by Kairos Power, take extreme heat applications further by relying on a radically different fuel architecture. Instead of heavy metal fuel rods, they use microscopic precision. The fuel is housed in tiny, dense ceramic spheres known as triso fuel pellets. Looking at an exploded view of a single triso particle, you can see the uranium core at the center. It is surrounded by structural layers of carbon and strong silicon carbide ceramic shells. As external temperatures spike in this heat map, the central core remains completely contained. The layered ceramic coating retains all fission products internally, even at extreme temperatures and in the total absence of active cooling. By pushing containment engineering down to the microscopic level of the fuel pellet itself, designers can safely eliminate heavy macroscopic barriers, radically simplifying the cost and structure of the overall plant. The ultimate deployment goal looks like this: a fully operational SMR plant venting continuous steam from its secondary loop, running directly beside the cooling fans of a massive data center campus. To secure this continuous power, large technology companies have collectively committed to over 10 gigawatts of new U.S. nuclear capacity. This photograph of the 3 Mile Island cooling towers highlights the urgency of that demand. Microsoft signed an agreement to restart an idle unit here, proving the immense market appetite for legacy firm power. Tech giants are also making specific bets on modular designs. Meta has agreed to fund TerraPower Natrium reactors, and Google signed the first corporate SMR fleet deal in the U.S. with Kairos Power. This momentum extends to the ground. Across the historic Oak Ridge complex seen here, Kairos has already broken ground on the Hermes demonstration reactor. Structural engineers are already inspecting freshly poured foundation pads and checking survey marks. The technology is transitioning from digital blueprints to concrete reality. These tech giants are financing the early, high-cost phase of the manufacturing curve, effectively forcing a new industrial supply chain into commercial existence. Translating that capital into physical reactors requires rigorous logistical planning, down to engineering teams marking hold points on large-format assembly drawings. At staging areas, workers check flange interfaces on factory-fabricated module sections, verifying the physical tolerances before final site assembly. The economics of this transition remain unproven. SMR cost reductions depend entirely on high-volume factory manufacturing, a scale that does not yet exist in the commercial market. There are severe supply chain bottlenecks requiring sustained investment. Heavy forging for pressure vessels, advanced control system fabrication, and mass triso fuel production all require a massive industrial scale-up. There is also regulatory friction. Reviewing a construction permit means navigating thousands of pages of safety cases. Licensing remains a multi-year hurdle for any new design. Despite the influx of capital and the optimization of reactor physics, engineering physical infrastructure takes time. The most credible timeline for commercial SMRs to begin delivering power to the grid sits squarely in the 2030 to 2035 window. To understand the thermodynamics and structural specifications driving these next-generation reactors, you have to read the technical documentation. Visit ProReadyEngineer.com to explore the engineering behind the grid of the future.